Hello everyone, welcome back to our channel. In this video, we are going to learn about the implementation of all the logic gates using only the NAND gates. Let's move with it. So, before going to the implementation of the logic gates using NAND gate, first we need to understand some of the Boolean laws and theorems. So, the main important Boolean laws are, the first one is the identity law. This identity law will say that when A is added with 0, the output will be always A, and A is multiplied by 1, then the output is always A. Then the second law is null law. The null law is state that when A is added with 1, here the 1 is dominated and the output will always 1. And when A is multiplied by 0, always the output will be 0. This is like the normal multiplication. When anything multiplied with 0, then the output will always remain 0. The third law is dependent law. This states that when A is added with A, then output is A. When A is multiplied by A, then also the output is A. Fourth important law is complement law. This states that when A is added with the A complement, always the output is 1. Similarly, when A is multiplied with the A complement, always the output is 0. This is the main important law that you need to remember always throughout your sessions. Okay. Last one is double negotiation. This is also very important law. They state that when A complement to the whole complement, it is like a double complement. A complement is like a negation of the A. A double complement is negation of the A complement. So always we are going to get A for A double complement. So the next one is the De Morgan theorems. These De Morgan theorems are very important theorems while converting any equations to write only by using the NAND or NOR. So there are two most important theorems for converting the expressions. They are A dot B whole bar equals A bar plus B bar. So here you can able to see A dot B whole bar will have the operator as dot, which is nothing but the multiplication. So A dot B whole bar is converted as A bar plus B bar. Here the operator is changed from multiplication to addition. In the similar way, A plus B whole bar is equal to A bar dot B bar. There is an alternative way for it also. That is AB equals A bar plus B bar whole bar. In the above conditions, you saw that A dot B whole bar. But here we have only AB. So that is equal to A bar plus B bar whole bar. The same way, A plus B equals A bar dot B bar whole bar. Here we're not going to prove how it come and all those things. We just remember this theorem equations which is already derived from the De Morgan theorem. So why we need this De Morgan rule? Because they help us to convert AND into OR. If we have any AND equations, we can able to convert that into the OR equation and vice versa. If you have OR, then we can able to convert it to AND equations. And they make complex logic circuits simpler. Okay, that is the second point. Then third point is they help us to design all the logic gates using only NAND or NOR. So they are used to reduce the number of gates in the circuit. That is the one advantage. And they are useful in K-map simplification and logic proof. The K-map related things you're going to learn in the further part of the videos. Now, they make digital circuits design and programming easier. Let's move with the implementation of the logic gates using only NAND gate. So, we are going to design total as 6 logic gates by using only NAND gate. They are NOT gate, AND gate, OR gate, NOR gate, EXOR gate and EXNOR gate. These are all the 6 gates that we are going to design only by using the NAND gate. Let's move one by one. Let's consider the NOT gate for first. A NOT gate always produces the complement of its input. So it is act as a inverter. The Boolean expression for the NOT gate is y equals A bar. And you already know the logic symbol or the logic circuit for the NOT gate, which has a triangle with a bubble. Here the truth table is also provided for that. That is, when input is 1, then the output should be 0. When input is 0, the output should be 1. So let's move with the implementation of this NOT gate using only NAND gate. If both the inputs of a NAND gate are connected together, then the output becomes the NOT of that inputs. This is how we are going to design the NOT gate by using only NAND gate. Here we have only one input. NAND gate will take the two inputs. So we connected the single input to the two inputs of the NAND gate. So we get the complement of the input. So this is how the NAND gate will work as a NOT gate. Let's move with the AND gate now. We know that an AND gate gives output 1 only when both the inputs are 1. So you already know the Boolean expression y equals a dot b, and the logic circuit is also given here, and the truth table for the AND gate. We are seeing output 1 only when both the inputs are 1. So let's design it by using NAND gate. So while designing the AND gate by using the NAND gate, we should remember what is NAND gate equations. We have the NAND gate equation as a dot b whole bar. So we need to invert the NAND result in order to get the AND gate. So the final Boolean expression for the AND gate by using the NAND gate will become like a dot b whole bar to the whole bar. The final circuit will look like this. Here we have the two NAND gates, one having the input AB. So it providing the output as AB whole bar. That AB whole bar will become the input for the second NAND gate. That NAND gate will complement the input what it is receiving. So AB whole bar will have another complement at the output. So it become AB. This is how the AND gate is designed by using the NAND gate. Here we are using two NAND gates in order to design a AND gate. Let's move with the OR gate. An OR gate output is 1 if at least one of its input is 1. So here we are considering AB. If either one of the input is 1, then always the output will become 1. So Boolean expression is y equals a plus b. So when we move for the implementation of this OR gate using only NAND gate, we must consider the real equation of the OR gate, that is y equals a plus b. Based on the De Morgan's rule, we know that a plus b is always equal to a bar dot b bar whole bar. So if we can generate a bar and b bar, then NAND them together, we get a plus b. So final expression will look like, we already know that a dot a is always a and b dot b is always b, based on the Boolean rules that we have already studied. So the final expression for the implementation of OR gate using NAND gate will look like a bar dot b bar to the whole bar. This is how the expression for the OR gate by using NAND gate will look like. Then move with the circuit. This is how the circuit of the OR gate will look like when it is constructed only by using the NAND gate. Here we have three NAND gates. First NAND gate is for A complement, second one is for B complement, and we are taking these outputs as the input for the third NAND gate. So we are going to get A bar, B bar, whole bar. Here you are converting the OR based equations to AND based equations. So we must go with the De Morgan's rule. Based on the De Morgan's rule, you can able to convert any logic gates to any logic gates. So let's move with the other gate, that is NOR gate. In NOR gate, we know that a NOR gate gives output 1 only when all inputs are 0. In the truth table, you can able to see that where it performs the NOT operation on the OR output. Yes, we already studied the OR gate. So NOR is the complement of the OR gate. Right? So the Boolean expression for the NOR gate is y equals a plus b whole bar. So let's move with the implementation of this. So the expression for the NOR gate, that is a plus b whole bar. So we can able to simplify it as a bar dot b bar, which is based on the De Morgan's rule. So the final expression for the NAND based NOR gate will look like a bar dot b bar whole bar to the whole bar. So this is a circuit what we are going to see after designing the NOR gate only by using the NAND gate. Here we have total 4 NAND gates. The first NAND gate is for the A complement and second NAND gate is only for the B complement, and we are taking the outputs of these two NAND gates and giving these two outputs as the input for the third NAND gate. So by giving the inputs A bar, B bar to the third NAND gate, we are going to get A bar dot B bar whole bar. So here we want A bar dot B bar, that's it. So again complementing it will give rise to the A bar B bar whole bar whole bar. So double complement for A bar dot B bar, so that we are going to get A bar dot B bar, which is equal to NOR gate. Let's move to the next gate, that is XOR gate. The output of the XOR gate is always 1 only when both the inputs are different. So the Boolean expression is Y equals A bar B plus A B bar. Let's move with the implementation. So this is how we are going to design by simplifying the equations of the XOR gate by using the De Morgan's rule and the basic Boolean rules. So here we are considered F equals A bar B plus A B bar. This A bar B is the basic equation of the XOR gate. We are taking the complement for all equations. By that we are going to get F complement equals A bar B plus A B bar whole bar. Let's consider this A bar B. So that we are going to get like A bar B equals A bar B plus 0. Here when we go for the 0, anything which is added with 0, we are going to get the same value. So A bar B plus 0. Here we already know the Boolean rules, that is anything is multiplied with its complement is always 0. B dot B bar. So we can able to easily take the B as the common and we are going to group A bar plus B bar. We can able to easily write like A bar B is always equal to B of AB whole bar. This A bar plus B bar is converted to AB whole bar based on the De Morgan's rule. This is considered as the second equations. So let's move with this A B bar. This A B bar we can able to write it as A B bar plus 0. Between A and B bar we are considering here, so that we can able to simplify easily. So we are taking A as common between this and we return A of A bar plus B bar. Based on the De Morgan's rule, we wrote it like A bar plus B bar is always equal to A B bar. So the equation for A B bar will look like A of A B bar. So this will become the third equation. Now let us put this equation 2 and equation 3 in the equation 1, that what we have. The first equation is F complement equals A bar B plus A B bar whole bar. So by applying this equation 2 and equation 3 at equation 1, we are going to get like F complement equals B of AB bar plus A of AB bar whole bar. Here we have the F complement, but we need only the main equation F. So again complementing it will give F double complement. So F double complement equals B of AB bar plus A of AB bar double complements will give F equals B of AB bar plus A of AB bar. F equals B of AB bar dot A of AB bar. So based on the De Morgan's rule, that is AB equals A bar plus B bar whole bar. So that this F equals B of AB bar plus A into AB bar will look like F equals B of AB bar whole bar dot A of AB bar whole bar, and the whole equation will finally have the complement, so that we are going to get F equals A bar B plus A B bar. So this is the advantage of the Boolean rules and the De Morgan's rules, so that we can able to convert any expressions as our requirement. So the logic circuit will look like this. We have total 4 NAND gates here. So in the first NAND gate, we are taking AB as the input and we are getting AB bar. Let us consider each part of the equation. In the first part, we have B of AB bar. So let us consider B as one input and AB bar as the another input, so that we are going to get B of AB bar whole bar. Similarly, with respect to A, we are giving A and AB bar as the input to the third AND gate. We are getting A of AB bar whole bar. So the output of this second and third NAND gate will give on to the fourth AND gate as the input. So we are going to get the final expression what we want, so that it becomes A of AB bar whole bar dot B of AB bar whole bar. This is how the expression and the circuit of the XOR gate will look like when we design by using only NAND gate. Let's move with the XNOR gate. So in XNOR gate, we already know that the XNOR gate gives output 1 when both the inputs are same, either both 0 or both inputs should be 1. So it is the complement of the XOR gate, so that we can able to design the same circuit like when we add the another NAND gate for the XOR gate, we are going to easily get the XNOR gate. So Boolean expression for this XNOR gate will look like y equals a bar b bar plus ab. Let's move with the implementation expressions. So we have the XNOR gate expression, that is a bar b bar plus ab. So we are considering f equals a bar b bar plus ab. So we are taking the complement for it, so that it will become like f complement equals a bar b bar plus ab whole bar. F bar equals a bar b bar whole bar plus ab whole bar. This is based on the De Morgan's rule. We already taken the complement for the main equation. So again taking the complement will give the original equation, so that we are again taking the complement for the f complement will become f double complement, so that it is equal to f. So the finally we are going to get f equals a bar b bar whole bar dot ab bar whole bar. This will give rise to the XNOR gate by using only NAND gate. So the circuit will look like this. In the first NAND gate, we are taking the AB as the input, so that we are going to get AB bar, and we are complementing A and complementing B in the second and third NAND gate. From the second and third NAND gate, the output is considered as the input for the fourth NAND gate. As the input for the third NAND gate is A bar B bar, the output will always become A bar B bar whole bar. And the output of the fourth NAND gate and the first NAND gate will become the input for the final NAND gate, that is fifth NAND gate, so that the output will become A bar B bar whole bar dot AB bar whole bar. This is how the circuit of the XNOR gate will look like when we design by using only NAND gates. This is the summary what we have designed till now. We have designed NOT gate, AND gate, OR gate, NOR gate, XOR gate, XNOR gate. So these are all the Boolean expressions that what we have derived till now by using the Boolean rules and the De Morgan's rule. And here the number of NAND gates we require in order to design that particular gate. For the NOT gate, we require only one NAND gate. For the AND gate, we require two NAND gates. In order to design the OR gate, the minimum number of NAND gate required is 3. NOR and XOR gate is 4. So finally, XNOR gate will require minimum 5 NAND gates in order to design. So this is all for this video. Don't forget to subscribe our channel. Let's meet in the next video. Till then, bye.